In a previous video, we had looked at this half ring structure, cantilevered at both ends, planar structure with a load F in the plane. And the question was, what are the redundant supports and what is the deflection at the point of the load F in the vertical direction? Before we can find the deflection due to load F, we're going to have to first deal with the redundant supports. In the last example, we actually replaced this redundant set of supports with the equivalent reactions at this support. An outward load, a left-right load, and a moment. In this case, we're going to work it again. Excuse me. But we're going to save a little bit of effort by looking at only half the problem, recognizing that we do have some symmetry. Okay. And so we're going to cut away half the structure and replace this half of the structure with what goes on here. And what happens here is this point is able to move up and down, okay? But because of symmetry, there is no slope at the point where the load is applied. This slope of the structure always remains perfectly level at the point where the load is applied. But because of that, we are going to have left-right reactions here, left-right reactions here, so we must also have a left-right reaction right here. And so we will replace, or we'll make a cut in the structure, and the behavior of that structure will be a guided cantilever, and that guided cantilever is able to provide a left-right reaction. It provides a rotational or a moment reaction, but it doesn't provide a vertical reaction. Okay, and so what we'll do is we'll now take this reaction, which is redundant. Again, statics would not let us solve for both the reactions, for any of the reactions here or here. So we're going to have to use strength of materials. So we'll throw out this reaction and replace this reaction with the equivalent reactions. Or we're going to throw out this support figure, replace it with equivalent reaction forces. There are two of them. So both RB and MB are redundant reactions. We're going to write our energies for the structure in terms of RB, MB, the applied load F. We'll integrate over the entire quarter ring, and that will give us deflection equations. We're going to write three different deflection equations. We're going to write a deflection equation based on MB from Castigliano, which would give us the slope based on MB. We'll write a deflection equation based on RB, which would give us the left-right displacement based on RB. And we're going to write a deflection equation based on F, which will give us the vertical deflection. Okay, we don't know the vertical deflection. That's what we're really after. But we also don't know the reactions in these moments. But we do know what really happens because of these reactions in these moments. This moment will be strong enough to keep this slope zero. This reaction will be strong enough to keep this point from moving to the right. Okay, so the deflection because of RB is zero. The slope because of MB is going to be zero. So we're going to write two equations to solve for these reactions, and finally one equation to get the deflection. To do that, we've got to write the moment everywhere. The moment in the beam as a function of theta, coming from an RB contribution, is again our old friend, the 1 minus cosine theta term. The moment at this point, because of load F, we'll have this moment arm, which is an r sine of theta term. I called the RB term positive, so we're going to call this F term negative. We're going to call the MB term positive. So it's a minus F times r sine of theta plus MB. That's the moment everywhere within the ring as a function of theta. We're going to take three partials, RB, MB, and F. The partial with respect to RB is going to be r times 1 minus cosine of theta. The partial with respect to MB is going to be a positive 1. And the partial with respect to this load F prime is going to be a minus r sine of theta. Now to solve the problem, and this is very schematic and it's leaving out all the hard parts of the integration, but that is just calculus that can be done. It says the deflection because of the load RB is 0. We know that. We know that this point, when we load it, does not move left-right. So RB has to be strong enough to keep this point from moving left-right. We also know that when we push down on this point, because of symmetry, there's no slope at that point. So this MB must be strong enough to keep this thing coming straight out, even when it deflects downward. We know those two deflections. So we say that the deflection in the direction of RB due to RB is 0. But from a Castigliano point of view, that's equal to the integral from 0 to pi over 2 of m of theta times the partial with respect to RB times RD theta. Notice because I've set it equal to 0, I've left off the 1 over EI again. We can divide that out. Same thing is true, the deflection due to MB, which will be a slope, gives a 0 slope. But that's equal to this Castigliano term, integral from 0, not 2 pi, pi over 2, that's a mistake, of the moment from the above equation multiplied by the partial of the moment with respect to MB, and that was a 1 that goes here. The moment equation here goes here, the 1 goes there, RD theta goes here, that's equation number 2. We take this thing, the big ugly mess that it produces, set it equal to 0, and when we're done we can solve this one for MB. When we're done with this one we can solve it for RB. We now know our reactions. Then finally I want the deflection at the load F. And that deflection is 1 over EI. I'm not going to be setting this one to 0. I actually want to solve for the deflection. It's 1 over EI. The moment equation from above, put right here. The partial of the moment with respect to F, which was, where is it? Right here. Minus R sine of theta. Minus R sine of theta goes right here. RD theta. We integrate this thing, and what we're going to get out of it is a term that involves F, but it's also going to involve MB and RB. But we take the definitions for MB and RB that we acquired up here, plug them into this equation, simplify, and we will get the deflection at point F where the load is applied in the direction that the load is applied. I again have MathCAD documents that do all the number crunching, and I will be making videos explaining those MathCAD documents. In the end, what we do see out of the MathCAD documents is to make this problem and this problem equivalent. This load that I apply here, called F prime, has to be the same as this F divided by 2. And so, because I've calculated the deflection for an entire load F, this equation gives me a deflection for an entire load F applied there. To compare it to my earlier solution from the previous pages, I've got to divide that by 2. And we'll see that in the MathCAD.